it could be, again, about half of what needs to be done won't be achieved even with the Paris Accord. So there's a huge pressure there, and I think everyone, and especially anyone who's thinking first is here. And of course, since then, since the Paris Agreement, there's also then been the fact that realizing there has to be these very drastic reductions in the CO2 if we're going to try to meet in fact, a 1.5 degrees Celsius increase is almost hard to imagine that it could be achieved, because it would take 45% decline by 2030. So really, not much more than, well, really not even a full 11 years to try to make those kind of reductions. But even the 2 degree pathway, we have some great challenges. So I think what we're seeing here is that, sort of the, and as I said, those that are looking forward on this, and this is particularly, I guess, the large, if you're a CEO of a large multinational and you want to be in business 30, 40, 50 years out, how do you position your company to do that? That's the kind of thing. And so there's certainly this concept now that we really need to move towards really more fundamental, it's called change of more disruptive ambition. So instead of just seeing, oh boy, look at the greenhouse gas emissions to run rail freight, they might say, well, why don't we electrify the rail system? And again, really disruptive things and suddenly change systems as opposed to just tweaking them. And a key part of this then is now beginning to really recognize that the land and the agriculture that takes place on the land, the so-called AFLU sector, the agriculture and forestry, and all other land uses, represent about 25% of emissions, and also has this huge challenge that we have to feed at least 9 billion by 2050. So now there's again renewed interest, heightened interest, I guess I would say, in using this the land and switching it from seeing it as a sort of a problem to really start to see it as a solution. So how do we protect what we already have? And so the concept of avoided, grassland conversion, avoided forest conversion starts to become in. So paying for the maintenance of existing sinks is something now that is going to appear. Okay, sorry. And also then, how do we improve the management? So things like the 4R, nutrient stewardship, and all the things that, of course, we want to improve anyways in terms of things like feed use efficiency in livestock, improve manure management, improve cropping practices. All these things now need to be seen as well as how can we do to restore back with some of what we have. And so reforestation is one of them. We're targetedly saying maybe some of those sloughs that were drained are better off left as sloughs, and there'd be certainly carbon advantage to doing that. And so this could be a huge potential. And so again, there's a massive amount of interest, especially in the multinational corporate community, I guess in particular, in seeing how to make this work. So how do we price this to make it happen on the landscape? And we really have, and John went into good discussion of this, fortunately, but certainly in the compliance market. So that's your basic offsets, and that's where the emitter buys the offset from the non-regulated part of the economy, and then uses that offset to offset some of the large emitter emissions, and so the price there could be 15. So it's already $10 a ton, at least CO2. So it will rise to $50 a ton of CO2. And so it's, I guess the problem there, and we've seen it already, is if the policy changes, then this whole offset thing can fall apart. So, Ontario had been really big on developing an offset system, and then they just changed governments with the last election, and it's all gone. There's also voluntary markets, and John described ones like the Chicago Climate Exchange. Obviously that's, it's a little bit more fuzzy, but it certainly is one that you can play in. The price is generally not high, but it could be high depending if someone really wants those credits, and probably they want those offsets for some other reason, such as for its natural benefit or something, that they're willing to pay more, they probably just might see it strictly from a carbon point of view. But the problem there, of course, finding buyers uncertainty. But then what we're seeing more, or what we believe may be happening more, is what we call insetting of supply chains, where there starts to become investments in reducing greenhouse gas emissions within the company's supply chain, but even beyond the supply chain, even within the value chain that they're operating in. And so these emission reductions then become claimable by that company. The company's facing, of course, the same sort of carbon taxes and whatever. And so I was looking for that. And so this one called gold standard, science-based targets, carbon accounting instrument framework, and this is coming. And it's not just those necessarily buyers of the product, but also those that are in the value chain. So the fertilizer emitters, the chemical companies are also interested in investing into agriculture and getting some of the emission reductions. And so seeing this as inherently part of their business practice. And I guess that's still obviously under development. So how do we get the value proposition to everyone so that it all makes sense and all works? And it's fair for everyone. That's certainly a big challenge. And John again has outlined this whole thing of pricing carbon has many challenges, but now is the time to get involved and make sure that the value proposition does work for farmers. And of course, Alberta, I mean, it has had a lot of experience and many firsts, even though we can criticize it, but at least it was up and operating and providing a economy-wide baseline credit system. It is based to international standards for offsets. It has a number of methodologies, many projects, 40 million tons, and also those that didn't want to buy the offsets, of course, paid in at $15 a ton CO2, so that created a very large technology fund that has also been invested. And again, it's often been used as a model for others either designing or implementing offset systems. And the agricultural protocols, I mean, when you're familiar with the composting, the NERP, anaerobic decomposition, biofuel, emission dairy cattle, which, again, as it says there, usually adopted in Kenya. So, you see these things, how do we you get the animals to slaughter, beef animals to slaughter way earlier, that becomes a protocol, etc. And then, of course, the final one, conservation cropping, which is the one that really includes soil organic carbon, which is what I'm talking about. So it has many problems, but also it has worked and has been successful. So, as I said, this idea of becoming more embedded in the supply chain and the value chain is certainly, and it's often one of the great large movements has been science-based targets, where different companies take on and say, we'll take on a science-based target, and then those that are involved with agriculture tend to then logically look at their supply chain as part of meeting their obligations. But it's more than just necessarily the supply chain. It's also because most of the emissions from agricultural products, with a few exceptions, come really up for the farm gate. So if they're going to make emission reductions in their whole operations, including their supply chain, then the farm part of it is a huge part of the emissions, and so it becomes a big part of their motivation to make investments there. And as I said, again, this is where how to figure out the value proposition for everyone is the big challenge. So the idea is that this then will start to enable large-scale private sector investment in greenhouse gas reductions, but there's all kinds of challenges in terms of all the accounting and reporting, and also ensuring that reporting is transparent, I guess, to consumers and to society as well. much of the supply chain is referred to as scope 3. Sometimes you hear that word, and scope 3 just means those emissions. The scope is outside of the business itself. So Walmart, which has very aggressive corporate reduction targets, would do everything it can internally, but eventually scope 3 is how it does it through its supply chain. Make those reductions. And so, again, so a pretty major group of companies investing in some of this sort of work. And often one thing about it is they're looking really for common approaches are desired. And so the example would be this cool farm tool, which, that generally hasn't been shown to work all that well in Canada, but they really want to have tools that they can use globally. And this particular one has a number of different metrics or measures for water, carbon, biodiversity, and also economics. And now we're working on seeing if we can get it to work better within North America. And I guess the objective again is this traces sustainability through the supply chain. So, so this testing within Canada for testing in North America, starting in Alberta, and driven a lot by McDonald's and Alberta beef, and so McDonald's are kicking up a big chunk of the resources. So this, but this is something to sort of be aware of, is that they're not looking for a made in Saskatchewan quantification. They're very often looking for one that they can apply globally so that they can have consistency. So the challenge is then, I don't think I need to spend any time on this, but just that we know that in Canada right now it's a complete dog's breakfast, I guess, of policies around carbon, depending on which province you're in, and as well as that, there's been work within many of the provinces, for example, Saskatchewan, on offset protocols and whatever, so that there's a lot of things also that could be implemented probably relatively quickly if they wanted to. So it really then means it's hard then to price carbon, because if you're selling into Saskatchewan, which is facing at the moment anyway sort of a lower value of carbon than say BC, then all this is causing problems. And so tax trade, as well as Quebec still wants to maintain a cap and trade, cap the emissions and then trade, and let the value of the offset be sufficient to meet that emissions target. So, but of course there's huge challenges for agriculture. The nature of agriculture is being very distributed over large areas, and things aren't metered in the same way that the fuel consumption of the railways is or something. So it's harder to get the cost, and there's a risk that you get it wrong. There's a reliance on modeling and estimates, and that's good, but they tend to be very, very general. Each farm tend to have small reductions individually, but so the cost of quantifying this on scale remains a problem. So sequestration is potentially reversible. Go back to different practices. Then how does that? That's a risk from the buyer's point of view anyway. Revenue stream can be small, so again, scaling it, getting the cost down is important. Activities can shift, so I can shift where, so I can say, well, we're going to avoid grassland conversion here, but then somewhere else, someone says, oh, there's too much grass now, so I'll break my grass. I'm not in that program. I'll break my grass and protect cropland, so that's a leakage. And then additionality, John touched on this, can simply be difficult to meet. It can, in many cases, be arbitrary and really represent a barrier to making an offset system working. So, I think then the next part of my talk is really dealing with how do we improve the estimates of soil organic change by investing in soil carbon measurements. And this has come back up again, this sort of a realization that soil carbon is important. So how do we, what are the opportunities there for investment? And I'm really thinking here investment by producers, either themselves, I guess, or through organizations or through the checkoff commissions and so forth, but co-investing anyways. But what should be done in terms of measurements, or what can be done, or what was sensible to be done, I guess. I guess just to remember something about soil, it's very dynamic at the surface, and most in Saskatchewan in particular, majority of the carbon is in the top 30 centimeters pre-roll for all soils. And if you want to convert soil carbon to CO2, you just multiply by 3.67, so it's something to remember. Again, you can also convert soil carbon to an estimate of soil organic matter by 1.72, but soil organic matter is very heterogeneous. It could be anything from crop residues that I can see very clearly, that's a root, to some living microbes, to some humus that could be thousands of years old. Also, we've got to remember there's a lot of land that's tied up with carbon sequestration. So you want these very high rates of carbon sequestration, but then at the same time you're tying up a huge amount of nitrogen. You can get at that nitrogen by letting the organic matter decompose, but then you lose the carbon. So it's something to always remember, that carbon and nitrogen are inextricably linked. You soil organic carbon. Again, all carbon in the soil is what's CO2 in the atmosphere. And why would it change? It changes because something has happened that changes the balance between the carbon input to the soil and the loss from organic matter composition by soil microbes. And if you want to get a large change, then you've got to have a large change in that balance. So what we need to think about in terms of selecting the best strategies to support the quantification approach and purpose? Well, so if we're going to invest in soil carbon measurement, we really have to have an issue that we want to do. And usually the ones that I hear anyways are to think that what's now there is underestimating soil organic carbon increases. And so if it's doing that, then we want to fix that. No one complains if it happens to be overestimating, but that's the other. But certainly there's also concern. The other major reason would be to provide greater confidence in organic return for those who pay for the increases, whether it's paid through the value chain and the higher price for the product, or whether it's directly through an offset. But before we then take a measurement strategy that would address those issues, we really need to think about what is the quantification approach that will be supported. That's fundamental. And the other is, what is the purpose of the quantification approach? So in terms of quantification approaches, there's really three basic types. The first is a practice-based factor. I'll go into a little bit more detail on these. These are just a factor, or a coefficient, if you like, of soil organic change based on some known change, primarily from measurements or validated models for measurements that are applied to the specific land management practice change. So if I have land that's gone from no-till from reduced-till, I know that might sequester half a ton of CO2 per acre, say, then that becomes the factor, the coefficient. We can also have soil organic carbon process model based, and that can then deal with multiple combinations of management, soil type, and weather. So the process model captures all these things. And also then we can make it more site-specific, because it can capture some of the weather effects, yields, land practices, initial carbon, soil texture, things that are very local. And so it's different than a factor that way. And then, of course, finally is there sort of measurement-based soil organic change in land in some kind of project. This is an actual measurement of the soil organic carbon change itself. And really in this case, because you're measuring the change in land, you really don't need to know anything more about the land other than the exact boundaries, because you're saying that is the change on that land, however it was managed. I mean, you want to know how it was managed, I guess, in terms of your overall documentation, but strictly speaking, you don't need to know that. Okay, the factors is just a simplified representation of the real world. So here, just showing soil carbon changing after some management change. It goes up and it follows a classic curve, and then we can simplify that with a straight line. Let's call that the factor. One atom, know the total carbon change, just the area it's involved times that factor, and bang, it's got it. So it's very simple. So it's basically a simple model, really, a representation of reality. And again, you can derive them from observed changes. That would be the way the IPCC would do it. They can do it from process models. Anyone who's played with common VR out of the US, out of Colorado, that's all done in thousands of model runs to give you an estimate. for your particular practice change, or you can have some sort of combination or package, I guess, of models and measurements and things, and that's in fact what Canada does with its greenhouse gas inventory for soil organic carbon. And the practices can be very general, very specific. It could be direct seeding in Saskatchewan, it could be very low disturbance direct seeding, well fertilized applied time of seeding, on how many clay loam soil in the black soil zone, well fertilized cereal canola dominant rotation. So, but yeah, it sounds great. I can get down the factor to something, that's just like my farm. But the problem is then obviously you need then data specific to that kind of situation, and you may not have that supporting data to derive a factor. So they tend to be very general. So there's these many advantages. Certainly it's the simplest. Practice change itself is often simple to document, like the conservation cropping in Alberta is a practice-based system. They only audit really the practice, nothing to do with the actual carbon change. And then when you just have to combine that practice with a factor, you can document the whole carbon change. Relatively simple to use and understand. Linear rate, anyone can understand that, multiply it out. Or the comparative, if I do a factor from some other, for the same practice, but use an alternate method of deriving it, I can easily compare them. And I can certainly estimate soil organic carbon change in the future. But the biggest thing is, of course, is that once you define that practice, then everyone, and the soil organic carbon change factor that goes with that practice, that everyone who follows that gets the same number, right? So there's no allowance for the unique conditions of the farm. And also too, the practice changes over time. So you define it as direct seeding, and then now with say vertical tillage. Well, is that part of a low disturbance direct seeding system? Could be considered part or not, or so all those things come in. So you define the practice at one time, and then things have changed, and even just crop genetics, yield higher yields, and start to have an impact. Okay, a model, again, it models the in-soil processes of decomposition and stabilization and affect the inputs of organic matter to the soil. But it is definitely clearly a black box that is difficult to understand. And as a result, many don't trust soil organic carbon change estimates from models. And I think healthy skepticism is well founded because it's very easy to misuse a model. So the model must be properly calibrated, the soil conditions properly initialized to work for the model to work well. I often say that if you got a modeler, they can't get you the carbon numbers you want. You change your modeler. But if they do properly calibrate and document all that, then they really can't get around doing it. But I mean, otherwise it can be definitely played with, especially with initial conditions. And again, you really want to have that validated. So really the real world soil organic change measurements are really critical. And one thing that you discover in validating is they never predict changes in multiple sites perfectly using a common set of parameters. You can calibrate for any one site and do a very good job. Once you try to do multiple sites with the same configuration of the model, then you find that it never is perfect. And so the model is definitely clearly, as complex as it is, it's very much a simplification of the real world. But it has many, many advantages. It can certainly be standardized globally, and that's, I said, very attractive for multinationals. It's able to estimate expected future behavior of the soil organic carbon. That can model both with and without intervention conditions. They can take all these site-specific influences and include them. It's highly flexible. If another better model comes along, I've got all this stuff, I can simply plug it in and run it. It estimates the rate of change over time, something really that a factor doesn't do, especially if you don't have good observations behind the factor. And it's reproduced by anyone giving the same inputs and parameters, and some models also link the carbon nitrogen dynamics, so that's a very huge advantage. But it certainly has disadvantages. I mean, obviously it can be very incorrect if it's not done right. And also, I think a particular problem with our existing models has been the problem with perennial vegetation generally, in particular when you talk about multi-species pastures. In particular, it's really highly uncertain. A lot of this comes back to the roots And I mean, it's maybe not a problem so much with the roots, it's just we don't have a lot of good soil organic change measurements on these sort of systems to calibrate or validate the models. And he said those models are very much favored by both supply chain. And you got to remember too, they look at these things, say, what can I use in a smallholder situation? So McCain's in Canada, they look at these very large fields of potatoes, say in southern Alberta. Okay, I can do all kinds of things there, even measurement. But if I want to buy potatoes off these smallholder farms, I can't. I've got to have something like a model or factors. Okay, so then we finally get back and find the final methodological approach to quantifying soil organic carbon change measure based. And so, again, it's the only one that's essentially result based. It is measuring the result directly. Well done measurements are something the most widely accepted by all stakeholders, even the most skeptical environmental organization will trust well done measurements. There's no major assumptions about appropriateness. I mean, you're just measuring what you're measuring. And also can be, if I do this, I can certainly adapt the data support and factor a model-based cost. But the biggest con, of course, is the cost of doing it. You don't know the results until they're measured. It's relatively inflexible. The initial design constraints possible future modifications. So you got to kind of design it right the first time, but then it's hard to change. And I think it's important too. It is, in some ways, it's probably the easiest one to do, as I call deliberate biasing, I guess, by just picking where you sample or what samples you might discard right in the field and so forth. So I think you really, the integrity of measuring the carbon is really quite important because obviously it is destructive sampling, and so it is inherently non-reproducible. No one else can go back out, resample that, and get the same results, or show that your results were incorrect. And I used to think the totally measure-based approach was infeasible, but just 2 weeks ago, I guess, we saw this press release where the Australian are issuing offset credits, Australian carbon credit units for soil carbon. And this is from an entirely measurement-based approach. So looking deeper into their offset protocol, I mean, it's sort of the first one that with actual measured carbon change in individual properties that I've seen that's sort of been working beyond just the research scale. Oddly enough, only specific practices are allowed, mostly pastures. There's probably some policy drivers here because there's no reason to limit practices in a measurement-based system, but they are. The baseline is the initial carbon, but all other emissions, again, the nitrous oxide, the methane, are difference with and without, and those are done through models and factors, mostly factors. So I mean, it's not all measurement. It has a lot of factors as well. And they discount the amount to 60% probably of exceeding. I've got a slide that'll maybe explain that. This is sort of arbitrary. There's no scientific precedent. It produces increasing discount as the uncertainty of measurement increases, so there's an incentive to do a good job measuring. But one thing is that a measured change of zero, so if you actually measured a change of zero because of this discount, it actually would be reported as a loss of carbon. And also one thing they do is they put 50% in a buffer, so for the first three measurements, but then you can get that back if you can demonstrate there hasn't been a loss of carbon. So they're essentially discounting very aggressively at the start, but it's not saying that buffer you can't get at it, you can get at some point in the future. So what is that 60% exceeded? So I just tried to draw it out. It's a completely hypothetical example, but a typical normal, what we call normal distribution of soil organic carbon change with a mean of about 3. And in this example, the carbon credit would be about 2.7 tons of carbon per hectare. That would be about 60% of the expected values of that distribution. Would be larger than that. Now the classical scheme, and this would be the one that had been in other draft, protocols, or ones that had never really been applied, would be more classical scientific practice, whereas you'd say, okay, I got confidence limits if zero change is within those confidence limits, then I say there is no change. And so in this hypothetical example, these would be about the 99% confidence limits. If that were the criteria in the protocol, then the 0 falls within that. So in this case, it'd be no allowable credit. If it didn't happen to fall in there, the actual credit would be the mean, which would be 3 tons of carbon per hectare. But you can see the tremendous problem with the confidence limits, and very difficult. And so, in fact, I was involved in a study where we looked at how many samples it would take to get to measure the change in percent of carbon, not percentage units, but percent of carbon. And then it turned out that in a grassland situation, using the confidence limit approach, 95% confidence limits, it was pretty well hard, impossible to detect changes less than 10%. 10% is a lot of carbon when soil organic carbon is high. So, you know, it really means the confidence limits, you know, it's no wonder they never took off, because it was practically impossible to get it. And so this Australian system, you know, is the first successful protocol that I'm aware of that sort of worked, but the other ones were just too expensive, and there's risk. And so we'll have to see. So then the next part of it is, what is the purpose of that quantification? And we've certainly gone into offsets, but the problem with offsets is you need to have the with and without intervention baseline. So you need to do both, and usually you're intervening on the whole land area, so that your without intervention is usually hypothetical. And so that, what does that mean? Models and factors. So, you know, it's difficult. You know, the offset is quite constraining, particularly on a measurement based only. Australia's got around that by setting a baseline at the initial value. The supply chain reductions, it's probably going to be rather similar to offsets, maybe perhaps less rigor. Or if you just want to document emissions, then you really only need estimates of recent changes. Or if you're documenting soil quality, you just need to know how much carbon there is and whether it's changing. So, you know, that is important. So if we're trying to do measurements, again, if we're making investments in measurements and we're trying to support a factor-based system, I mean, the key thing is you don't have to measure the whole land area that's involved, that could be involved in that. You just need to you need to know what practices are done, you need to know what land types are being involved, and then you need to make measurements on those combinations, or understand what combinations are likely to be important, and you want to have, let's say, at least 10 high-quality observations for each expected important combination. And the measurements are intended specifically to be representative, so you do have some, you know, idea of that these are, and it's also desirable to have some ongoing measurements just to ensure that the factor remains valid. For the model-based, it's a little bit different, because the model is such a point scale. You're really trying to get very detailed data at a very small area. You really don't care so much now about representativeness. Really what you're trying to do is make sure you cover the full range of practices and land types for which the model will be applied, so that you can validate it and calibrate it, etc. And so in that sense, site selection can be easier than for the factor-based, because you're not trying to determine representative systems. Again, these are to have ongoing change measurements to make sure that as conditions change, and we are balanced. So for some models that simulate the plant growth, you know, changes to plant genetics would be one of those things. Then for the measurement-based approach, I mean, now this becomes a very thing. First of all, you've got to set and define and map all the land involved exactly, including the land that isn't an inclusion, a slough or rock pile or whatever. You say, no, that's not part of the land, you know, that I'm doing measurements on. And so it's, you know, some work there. The Australian system mandates the so-called random stratified random sampling, I guess, and we need to document all this. Requires an individual measurement plan for each property, which would be, in our case, a quarter section, probably, or field, and needs to follow protocol. And how it's going to deal with intervention minus and without intervention. So to measure the results and to become protocol specific. And so now it's just really a matter then of prioritization of measurements, identify which gap in current quantification is poor. So we've got a problem, we say this is poor, maybe you say the whole thing's wrong, it's all underestimating, whatever. But anyways, you prioritize those gaps, and then you think about, okay, what system of quantification am I looking for, and what purposes am I doing it for? And then you select the measurement system. So I've only got a few minutes, so I'll just very quickly run through a little bit on the prairie soil carbon balance project. Again, so we did resampling was done by this spring of 2018. And this is, again, we got a series of measurements from 99, 2005, 2011. So again, what are our objectives there? Well, how does it work for individual fields? How deep do we need to sample? Questions like that. This would be the sites, and we can see then, if you look detailed, you can see again the 18 popping up, so different sites that had different times of measurement, including a number with in 2018 now, we've got 90 sites. This would be, a benchmark for a small area, not much different than the size of this overall platform here. And so we're measuring with small offsets the amount of carbon. We learned that carbon is very variable even within an area the size of this platform. And so depending, even that shifting creates a challenge. These are the results from 2011, and which showed, again, an increase, sort of a decrease, it's not below 10 centimeters, and then increase, but also importantly, it just kept going on and on with depth. What are the results for this? Well, unfortunately, we don't have the analysis ready quite yet. It will be available soon, but we do know lots of things from PSP already. Due to that variability within the microsite, the small spatial offset caused enough uncertainty that we couldn't make any kind of reliable estimate of carbon change for one field. So you needed about 30 of these microsites, and you could discern the signal against this background spatial variability. But importantly, the overall method will not meet the Australian measurement protocol, so it does not estimate change rigorously for the whole field. It just takes one little benchmark within the field that wouldn't meet the Australian protocol. And because of that high variability, it's not really particularly good for model validation because it doesn't give you any detail, that kind of high quality detail from one site, the information you need from one site. You can best think of it as providing support for factors, for climate change, for the conversion to conservation cropping. So, to summarize then, my prediction is that emission reduction in the supply chain will become more important than the sale of offsets from the regulated to the unregulated to the regulated sectors. That's a big question mark, but I just think that this is the way the world has to go if it's going to meet these targets. I mean, tweaking around with offsets isn't going to do it. It has to become embedded inherently in the food we eat and how we do our business, all sorts of business, to meet these reductions. So that ambitious disruption. So the green economy emissions become business mainstream, which hasn't been there yet. So we look at emissions as it's shown here as a cost, I guess, and because once you put a price on carbon, it becomes a cost. And I guess the idea is now to switch that to see how can we do that. But again, they're going to need some quantification approach, but unfortunately that's going to push it towards modeling, I think. So my very prediction there would be that modeling will be the winner of all those approaches for a bunch of reasons. And so again, if we're going to invest, if you're going to invest, or your organization is going to invest in soil organic carbon measurements, know that they're expensive, so you need to be very strategic. You need to think about, what again is your quantification approach? Are you trying to derive factors? Are you happy with that? Do you want to have an individual farm measurement based, or are you satisfied with models, especially if that's enforced on you? So again, this is really the purpose of my talk, I guess, was really to get that understanding of what gives you understanding that there's just doing measurements isn't an answer. You really have to know what you're doing with those measurements. So with that, thank you. I don't know if you're going to handle questions, how much time we have, but thank you again for your attention.
Thank you, Dr. McConkey. Do we have any questions? Again, if you want a question for Dr. McConkey, if you could come to the mic and we have it. Jim?
Jim Bogan from the Arm of Francis, 127. You related to the Australia way of dealing with carbon. And everybody knows that they did away with their carbon tax. So are they looking of ways to get money to agriculture because they realize that agriculture is putting carbon in the soil? Is that why they're doing these measurements?
Again, I'm not intimately familiar with the Australian system. Just because they said they picked on certain practices, I think it's clearly a political or policy-driven pattern to it. They had even when they had the carbon tax, they were rolling out this system, and so I think also too, I mean, the producer community there was already aware of this system, and I think they wanted to be able to take advantage of it as well. So maybe this is an opportunity. I think there's lots of reasons why probably they have put it into place, but it is certainly interesting and quite unique. As I said, no one else has been able to really see. Certainly been lots of measurement-based protocols put forward, particularly by environmentalists who are always very skeptical about soil carbon sequestration. So they tend to make them very stringent and therefore impossible to implement.
104 Gravelberg. I'm not sure I understand this very well, but the change in percent of organic matter, does that have an exchange or a calculation that can turn that into tons of carbon?
Yeah, if I know the density of the soil, or you can estimate that. Yeah, if you know the exact change of carbon, soil carbon, then you can directly, mathematically calculate that an exact amount of CO2 equivalent.
Thank you.
Don O'Connor with Renewable Industries Canada. Brian, from my experience talking to the California regulators, and you were there, trying to convince them that soil carbon should be part of the soil chain, and that the challenges we've had in Europe, I would say there's a lot more people in the world who don't believe it's possible to build soil carbon than there are the people in this room that believe it's a big part of agriculture. What can we do to overcome that doubt out there about this is real?
Yeah, well, as I said, the one thing about measurements, and again, if it has to be, strategically designed, but measurements are the one thing that is, accepted by all stakeholders, and I think we are thin on the amount of soil and carbon change measurements, and basically limited primarily to some long-term field experiments, but the number of those has been dropping, and so we're getting less and less information from them, and maybe they, and then the other question always is, what's happening on commercial farm fields, which could be different than small plots, and so that was one of the things that the Price over Carbon Balance project was intended to put some of these things on commercial farm fields. So I do think there is a definite place for strategic measurements on commercial farm fields. I don't know without a protocol, so we can't sell into the Australian market without a workable protocol. I don't know about a completely measurement-based approach to soil carbon at this point, but certainly having some more detailed measurements on some commercial farm fields that they could be either used to validate or improve factors or improve models, and also just on their own, of course, they become a valuable tool to convince the skeptical that in fact there are increases in soil carbon. I think measurements are really the only way to address that skepticism.
Yeah, Bill Warrington, 322. I understand that you have very wide variations in the carbon values when you do it in a test. On a quarter section, how are we going to come up with an absolute proof of how we say we've increased in carbon when it seems to be that things can change so much? You were talking about just on the top of that stage, you could have quite a bit of stuff. So.
Yeah, well, that protocol, of course, was kind of assuming there wasn't that much variability at those small scales, and so that specific offsetting did that. I mean, if we had spread those samples over a larger area, we probably still have the same spatial variability, but now we'd be getting measurements over that larger area. And if we did a few more over a larger area, which would be more or less like the Australian
So
system,
then-
then we can make those assessments. There will be variability there, and that's for sure. And that variability in the Australian system would affect how much you get from the protocol. You want to reduce that variability. You'll never ever get it to zero, especially with salt carbon.
Like, I've got some very well, some pasture that's not too far from me, and it's never been broke. So, I mean, there must be some carbon been stored there for a long time, and I mean, how would I get any credit for that?
Well, this is where things like the avoided to grassland conversion is really being looked at much more seriously. They're sort of saying if there's land that is under pressure to be converted to cropland because it's you're getting out of cattle or cattle are dropping or whatever, and you say, boy, I could get a few good crops off that. Then there's interest in if you can demonstrate that condition, then saying, okay, we'll pay you to maintain it into grassland. That would be the way. Same thing with avoided conversion, avoided wetland drainage, things where you could show and document that these would, if without an intervention, without some payment, these would likely be converted. Then that's the vehicle to get resources for.
Thank
this.
you.